Thanks, Vijay, and thanks for a nice intro. Okay, so like Vijay said, I've been at NYU. I've been at NYU now for almost 6 years since I completed my PhD here. And a lot of the work I've been doing there is using urban data or data from cities, right? And in this talk, I'll basically talking about a visual analytics framework that we are building to analyze this data. And also that's going to be the first part of the talk where I'm going to show a few demos of our tool. And in the next part of the talk, I'm going to talk about how you can, some of the database aspects involved in having such a tool, right? So what we are interested in, there's a lot of data coming from cities in general, and especially New York City. So at least for New York City, so we have data corresponding to the infrastructure, which is like the actual geometry of the buildings, the road network. And in addition to that, even other kinds of infrastructure like transportation. So for example, the taxis, we have a lot of taxi data, subways, the timings of the different subways at different stations. We also have data corresponding to the environment, like how much snowfall or how much rain has been there. And again, related to the environment is also we have data about complaints from people. Like, for example, due to harsh winters, say there's ice on the footpath, which makes it dangerous for people to walk. So people complain about those kind of things. Or there are potholes, there are holes on the footpaths and things like that, or noise complaints, right? So there was a recent article, I'm not sure where exactly, but you can just Google it, which says New York City, the city that never shuts up, right? So there's lots of noise that happens in New York, and we also get complaints regarding that. So we have a lot of data corresponding to the environment. And of course, we have data corresponding to people or social media, right? So we have data from Flickr, Twitter, or a lot of others like Instagram, and even they kind of release data, though not publicly, to some persons for research, right? And the goal here is, or at least what I'm going to talk about right now, is a specific visual analysis framework that we are developing called Urbane that is catered towards architects and city planners. So we want to make use of all this data that's available to better understand the city and see how you can frame policies, new policies for the city, or look at how existing policies work with are working and things like that. And in particular, we have been building this in collaboration with an architect firm called Con Pedersen and Fox. So we work with a few architects over there who work on the research division of KPF, and we have been iteratively building this tool, right? And yeah. Yes. No, so complaints, so New York City has this thing called 311. So similar to 911 for emergencies, for non-emergency complaints, they have this 311 number. So you can actually call them and then raise a complaint, and each complaint that's raised is stored, and then they also make it available as part of the NYC open data. Yes, yeah. Text, it's like a CSV file. You get the location of the complaint, the time, the complaint type, and any other metadata that text has stored. So they have different categories, like, so noise is one, and then you have the IC pavements is the other, and in winter, for example, if there is overheating or there's less heating, so there are even complaints for that. People can complain, and then things like that. So at least, yeah, so we have been working with KPF and we have been developing this tool. And I'll be focusing on two high-level questions that they are interested in answering, right? Uh, so the first one essentially is like, how does some new construction or new development impact the city? And this might not be true for all cities, but at least in New York, a simple example is something like there are these different towers that are coming up. There are really tall towers coming up. And one of the things that people are interested in is how does new towers affect the impact of views to other buildings that are already there. And in a very simple sense, this would be something like people would have bought some nice apartment because it has an amazing view over there, and the view adds to the cost of the apartment. They would be paying millions of dollars, at least $2 or $3 million for an apartment in a high-rise building to get these wonderful views of the city. And say a year down the line, there is a new tower that comes and blocks it up, right? So that's not preferable. And and it's not just about views. Even the city is interested in other kinds of analysis. Like you again have these tall towers, so it's going to cast more shadows, and especially if there are some parks nearby, and you need direct sunlight for good vegetation over there, for healthy plants and trees. So if this blocks it, they are even afraid that this might also cause some adverse effects on the parks. Or there are other kinds of impact, like how much of the, again, related to sunlight is how much of the sky you can see or how much is obstructed. There are places in the city, especially near Wall Street and so on, if you go over there, you will not get even a single minute of sunlight any time of the year, right? So it's so dense and clustered that if you look up, you literally cannot see the sky. So they're also interested in something like the sky exposure and these kind of things. So how does the new construction impact the city, right? And so let me just show you how some of the things that we are answering, at least for these kind of questions. So this is the tool that we are building, and I hope the flicker is not too much. Right. So for example, so here, in case of the say I'm interested in changing some building with some other building, right? So maybe this is a really old building and I want to construct a new tower over here. So what I can do is I can replace the building. In this case, what I'm going to do is I'm going to put just a simple tower. Right now, you can load any OBJ file, which is a standard format with whatever complex geometry you have, right? So now this new tower over here, it is thinner than what is existing, but it is taller. So how does it impact views to say some of the landmarks? And so you can select landmarks of interest. So here I'm choosing the Freedom Tower, and then say this is something like a nice building. I think there's a church over there. And I want to see how this impacts, say, the view, the new tower impacts the views of other buildings to these towers. So I can compute this over here, and then I see that, okay, so here we are giving a binary kind of visualization, but if you're interested and you want the actual values, you can also export it. So here what blue says is the views to these buildings have improved because of the new tower, and the red says that the views to these have decreased, right? And so essentially, I mean, it is in a way understandable. If you look at some of the towers over here, they are much, or the buildings over here, they are much smaller, or they are lower in height. And since the earlier tower was broader, it was blocking all the views. But now, since it's become thinner, the views have increased to a certain extent. Whereas in this case, they are already tall towers, and because maybe the height has increased, it has blocked, again, some of the view that happens over there, right? So this is one kind of impact analysis that you can do. And the other is essentially, let's talk about sky exposure here. So like I mentioned, what we want to compute is the amount of sky that is blocked up. So this color map here basically shows the amount of, when you look up from the street, how much of the sky is that, how much of your view is blocked by buildings, right? The fraction of the view. So it's a value between 0 and 1. And some of these places here, like Lower Manhattan and near Wall Street and so on, you can see that it's really dark, seeing that most of the sky is kind of blocked out over there. But in this case, it's a relatively open area. And if you want to see how it actually impacts, you can again compute it right now. And then there's actually not much impact. I mean, here again, the color scale, I'm not showing it right now. So a red basically means that the sky exposure or the fraction that's blocked has increased, but the increase is very slight over here, right? Because it's become taller, you see that the increase is very slight, whereas beyond one block away, there's almost no increase, which basically says that it doesn't affect the view over there. So, and the next question, so now, okay, so this is with very specific to when I have new development in some area and so on, right? So the next question obviously is how can we identify good areas to have new development or even in general, so that, so this is a particular question like the architects are really interested in. So how can I identify plots that has potential for development where I can make a lot of money? Essentially everything boils down to money. Or from a city planner perspective or the city agency's perspective, they can also see how do different neighborhoods behave, what are the properties of the city over different neighborhoods. And so how do you get these properties? So these properties can be obtained from the open data, the urban data that's available. So for example, if you have a place where there's a lot of good public transportation and there's always availability of taxis, then people would want to be in a place like that because it's easier for them to commute. Or if a place has lots of noise or lots of crime, then people would hesitate to move over there. Or even if or even if a new development comes there, you would the cost is going to be lower than otherwise, right? Or again, so if you have from a city planner perspective, if they see some like some place having lots of noise or lots of complaints, say regarding heating or with icy pavements or things like that, then they know that there's some problem over there and they can try to fix it, address it, and again see what's happening or frame new policies so that such things can be avoided in the future, right? So the second part of this tool is basically to kind of understand the city or look at the city in the context of these different data sets and compare different parts of the city using this. Let me just insert this. So you can do analysis on multiple kinds of ways. So the simplest thing is let's just visualize this data or different data sets over the city, right? I mean, this is something like what many of you might have already seen. It's a simple heat map visualization of the city. So here I've already loaded a few data sets. So I have like the crime that happened in New York, the noise complaints, the number of restaurants, number of, and the different schools that are there and the ratings of those schools, subways, where the subway stations are, and the taxis, right? And some of them are like static, like the restaurants or the schools and the subway locations. They are kind of static data, whereas the others are more like temporal. There's also a time component. The amount of taxis is going to change based on time, or right? So the simplest thing you can do is just visualize it as a heat map. And so for this, the query parameters that I'm using is, so I have data corresponding to 2 years, which is 2014 to 2016. And this is for 1 month of the year, right? So instead of looking at it something like this, you can also say look at a different resolution. Say I want to see how this is with respect to zip codes. So again, I have a, so I can visualize different zip codes over here, and what again I'm visualizing is the count of pickups, right? So the number of pickups that happen within the time range within each of these zip codes. Or I can again have a different kind of partition of the city, and this could be like I can choose over different neighborhoods, and I can again visualize the same thing. And okay, for those who don't know New York City, so these two parts over here, where there's a high number of count, corresponds to the airports. This is the John F. Kennedy Airport, and this is LaGuardia Airport. Right. And this, of course, is Manhattan, and this is Midtown, where a lot of tourist attractions are, like the Empire State Building, Rockefeller Center, all those. Over 1 month, right? And so instead, I can also change the accumulation time. So over here, for some reason my mouse is not working. I can change it to say 3 months over here, so that it's like the winter months of New York City, and see how the things are. I should have. And well, so the values would have changed over here. It's already recomputed. The values would have changed. It's just that the distribution still remains the same, so irrespective. So say instead of this, I can also visualize different data sets in the same way for the same time. So I can look at how crime patterns change in different parts of the city, right? And for those 4 months. So there are actually some regions where there are something like 3,000 crime happening in just 3 months. Or I can look at, say, noise complaints over here, and again, or even, let me go back to taxi data, because there are a lot of other attributes here. So instead of just looking at the count of taxis, I can look at what is, say, something like the average duration when I get into a taxi at these different neighborhoods, right? So I can again do this query over here, and you can actually see that the distribution of the duration is pretty different from the distribution of pickups. Even though there are lots of pickups in Manhattan, the duration is very small. So usually people take taxis only for short durations. And of course, from the airports, it's going to be a long duration and surrounding there, right? And this is one way of doing the visual analysis, or analyzing it, is by just visualizing this data. But you would also want to see how different neighborhoods are, or the characteristics across multiple data sets, right? So let me just, yeah, I'll come to that next. So that's the second part of the talk, as to why doing this is not as easy as what you're seeing right over here. So another way, so if you want to compare different neighborhoods simultaneously across these different data sets, then one visualization metaphor that you can use is called parallel coordinate charts, right? So how many of you are familiar with what a parallel coordinate is? Okay, so let me go into detail. Say, for example, I want to again compare taxis, subways, which are like two indicators for transportation, with noise and, say, crime, which is like you want lower value, right? So this is a parallel coordinate chart. So essentially what we are seeing here is the 4 axis, the y-axis over here corresponds to dimensions, or in this case, different data sets, right? So here I have a count of taxis here, the subway count here, the noise complaints, and the crime complaints. Not complaints, actual crimes. And each line over here, so let me just select Lower Manhattan, for example, right? So each line over here, so this bold brown line corresponds to Lower Manhattan or Battery Park over here. Essentially what it says is the number of taxi count is somewhere in this range, which is like a little more than 1 million. There are around 14 subways, stations in this region. The noise is around between 200 and 300, and around 500 crime that happens over here in the given query time period, right? And so essentially this is like high dimensional line, but you're just showing it here in 2Ds. So each of these lines corresponds to one of these neighborhoods. And this blue line that I'm showing over here is like the New York City average for all of these. So what it says is Lower Manhattan in particular has above average number of taxis available, way above average subway stations over there, again above average noise complaints, and it's on average crime that happen over there, right? And the advantage of using this metaphor is now what I can do is I can actually look at, say I want to see all neighborhoods that have above average subways. So I can select it over here, and you can see that all these neighborhoods have quite a bit of subways. But instead, if I just want to see above average taxis, there are very few neighborhoods where the taxis are available. So the rest of the neighborhoods have below average taxis. So it's almost like concentrated towards Manhattan, basically, right? And of course, you can also look at where there's a lot of crime. So really a lot of crime, and it corresponds to these regions. And what's actually surprising here is crime is pretty high in Midtown, and this is Chelsea, if I'm not mistaken. We don't have data. Okay, at least the crime complaints, I don't know, it depends on the data. So the data, nobody's complained from the park. Yeah. Okay. I haven't heard. Okay. Oh, the radial. Yeah. Actually, here, I think once you have the radial structure, there are some studies which actually show that I think the perception over there is much more, understanding that data is much more difficult compared to something like this. It's just different ways of visualization, but people are more, it's easier to understand this, or people have found it more easier to understand this compared to the other one. So, I mean, this is not something new. This has been used for more than a decade or two right now by a lot of people. So, just another standard metaphor. And at least as part of the framework, you can add new visualizations. If you want to visualize something just as a time series, so we do have something like that added over here, but I don't have it in this demo. So you can also do that. It's just a matter of what, and in our case, since we are working with architects, it's also something what they are comfortable using and what they find advantageous. So it was more like a design choice we made based on the advantages of having the actual users use this. And so this is just one level of analysis, and which allows you to kind of compare different neighborhoods, different zip codes, and so on. The other thing is now, say instead I've already decided I want to build something in Lower Manhattan, or I know a new plot in Lower Manhattan where I'm going to build, and I want to see the different properties and how it compares to other regions over there, right? So what you can do is, since I've already selected Lower Manhattan, I can go into a much higher resolution, which is the resolution of the buildings. And here what you see is essentially the same plots from the same data for each of the buildings. So these are unique IDs corresponding to the buildings. And you can do it, right? So for example, you see that there's a high concentration, crime is kind of concentration in one particular area. So you can select what that is, and they correspond to this particular region over there. That's almost near Freedom Tower, right? And so you can actually play around, look at how, so noise is kind of focused over there, and you can see how it kind of varies in different parts over here. Right. So again, so you can either look at the whole data from a macro level or much more micro level here corresponding to each of the buildings. And if you know, say, this is the region I'm interested in, then I can actually see in what range, say, the noise complaints are for that region. So it is somewhere in this range. So the noise is kind of on average for this new development over here. And of course, there are some data sets that are very specific to just building levels, like there's some regulation stuff. You can also choose this in the parallel coordinates if you want. So this is like FAR basically says how much, what is the maximum you can build for these buildings, right? So there are only few buildings there which allow, or few locations where the city allows you to build really large buildings or large towers. Okay, so no, that just the line is just says this is for the same region. So you know what the values are for this different region. So otherwise it's like a 4-dimensional point or a 5-dimensional point when you have 5 dimensions. So how are you going to visualize it? If you project it any other way, you're going to lose that context. You don't know what those values are. So the line is primarily indicates, okay, it corresponds to this particular, it's the same point. Yeah, it's just a connector. Yeah. Points on the axis, spatially? They are not spatially glued. What do you mean by? No, 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 no. The points on the axis are grouped, or rather, the grouping there is based on. I mean, it's the same point, so you can. It's based on the value of the axis, the range. Any other question? Yeah, I know. Okay, in Tableau, you can do analysis on something like the 2D kind of analysis to a certain extent. 3D is not allowed. So if I want something with everything around, you cannot do it, right? That's the simplest thing. And of course, the other thing is the spatial support for Tableau is more recent. So this tool it's been there for almost we have been building it for over 4 years right now. And the initial version of this tool, which architects started using, was like, it's almost 3 years old. Yeah, the spatial thing comes in much more recently, and there are other problems in any other tool that's over there which we have solved, which is the second part of my talk, which is more the database component of it, right? So essentially what you see here is different kind of queries a visual analysis tool can invoke. And so what we saw was there are two kinds of geometry queries that at least I showed in my demo. So these are like how do you compare view impact and how you can look at sky exposure and sky exposure impact. And the other type is more like the 2D spatial queries that you can have. So yeah. No, sky exposure just says, can I look at the sky or not? It has nothing to do with sunlight as such. Just, it's not going to change at any point, right? Unless a new building comes up. And the second kind of queries, which is going to be the focus of the rest of my talk, is spatial aggregation queries, a very specific type of spatial queries. And so all the visualization that were performed involves these kind of queries. So, so what do I mean over here? So here we have something like, yeah. Yes, there are a few like you can use. There are these GIS tools that you can also use, like ArcGIS and so on, to do some of these analysis. I'm not. Okay, it's been quite some time since I actually worked in ArcGIS. Again, I don't know what the latest version of it, what kind of analysis it supports. Yeah. Yes. And there is, again, for the 3D aspects, they have other tools which is separate, which you can actually do it. But one of the main problems we have seen with any of the tools that's already available is the flexibility in using the data. So you have to do, it's pretty slow if you want to do all kinds of queries. You have to do a lot of pre-processing to do it. So here, I mean, I'll come to that right now as to why. And again, so the Urbane tool is like, it's very specific to architects and city planners. So it's customized so that they don't have to look around working with different tools at different times. And the other thing that we also do is make it way more efficient than existing tools, right? And why do you need efficiency, and why you can't do these kind of queries easily in other tools, right? So for example, so here, this is the query that I'm going to be focusing on, and this is like spatial aggregation query. So here, this visualizations, what I already showed in the demo, is essentially the count of taxi trips in New York City for a given time period, right? So what is this query in a database parlance? So it's essentially you do a spatial join. So you have a set of points, which is like the taxi pickups, and you have a set of polygons, arbitrary shaped polygons, as you can clearly see over here. And what you're doing is you're doing a join between the points and polygons, and then you're doing a group by based on the polygon IDs, right? So this is a select whatever from two data sets where point is inside a polygon group by polygon ID, right? So this is essentially a spatial aggregation query. So when you're doing a single visualization, then you just have one query. But when you're doing something like a parallel coordinate chart over here, for each of the data sets, you need to run this query, right? So you have, in this case, you would have 4 spatial aggregation queries. Now, what can happen is, like in the tool, I can change the time that's involved. And then I have to rerun the query again. And or I can change the polygons that is there. So from neighborhoods, I can switch to zip codes, or I can go into the building level where it's a different, it's also a spatial aggregation query, but over there, what the join is, it's more like a distance join over there. So for each building, I look at all the points within a given neighborhood or radius of that building, and I have to group by that, right? So queries can change interactively, and since we are working with a visual analysis tool over here, we want interactive response times. I don't want to run a query, change something on the visual interface, and wait for a few minutes just to see how the changes are. I want it to be instantaneous, literally, right? I want the response given to the users to be instantaneous. That's one of the main goals of having a visual analytics tool, right? And so why is it so difficult to obtain interactivity when working with spatial aggregation queries? And to show why it is actually difficult, I'm going to use my favorite data set, which is the NYC taxi data. And how many of you know about this data? Okay, many of you do. Right. I mean, this is just one sample of the data, but all the other data sets that I use also have similar properties. So all of them, so at least in taxi data, it's really large, right? And so there are approximately 175 million trips. So each trip is going to be a point in our case that happens per year. And we have data for now 6 years or more, resulting in almost 1 billion trips. And for the demo, I used 2 years of data, which was like 350 to 360 million trips. And each of these data sets have a spatial as well as a temporal component. So, and in the taxi case, there are 2 spatial components, which is like the pickup time and the drop-off time, pickup location and the drop-off location. And there's also the temporal attribute, which is like the pickup time and the drop-off time, right? And some of them also have other attributes. So here, for each trip, we know what the fare is, what the duration is, how much was the tip that was given, and things like that. So if we took the crime data, then there it has just one spatial and one temporal component. So there's the time and the location where crime occurred. And it also has some metadata, which we are not interested right now, right? And so some of these data sets are really large. So here, 2 years of taxi, like I said, is over 350 million. And crime for 2 years, there were around a million crime or so, and a similar amount of noise complaints that happen over there. Actually, a lower number of noise complaints. So data sizes varies from really small to really large, right? So if you look at this spatial aggregation query, so let's look at the simple query wherein there's no time involved, and we are just saying aggregate all the count of taxis in each of the different polygons or the neighborhood polygons over here. The simplest solution that you can have is you can pre-compute the aggregation in this case. So as and when you keep getting the data, you just store it, and when visualizing it, you just have to load it and show the visual representation. So which is pretty easy and instantaneous, right? But what happens when I add a time constraint? So now there is a constraint which says t.pickup time is, say, in March. So this is 1 month over there. And pre-aggregation in this case is not going to work because you don't know what the time constraint the user is going to give. Unless you have predefined the times, it's not going to work. I can change it to any time over there, right? So you cannot possibly pre-compute all possible things. But that is where there are these data structures called data cubes. How many of you know data cubes? Okay, so there are these cube-based structures that are there, which in essence, given the set of attributes that are of interest, it tries to compute the aggregations across all possible values of the attributes, right? And this is commonly used in databases. And more recently, from a WISP point of view, there were structures which kind of improve the size. So one of the main problems of the data cube-based structures is the space or the space requirement, the memory required, increases exponentially with the number of dimensions you add, right? So there are structures like nanocubes and hash cubes which have added in a spatial component. So traditional data cubes didn't consider space, so these added a spatial component wherein they use a quad tree up to a particular resolution, and then they compute the other cube-based values, right? So these can be used to do this. But one problem, since they use kind of quad trees to do it, is that each query over there is basically just a rectangular region. And so if you have any arbitrary shaped polygon, you would have to run multiple queries per polygon. And it's still going to be approximate. You're not going to have it accurate. And it's okay being approximate, at least in a WISP perspective. I'll come to why it is okay. But even there, you have no control of accuracy, right? You don't know what it is choosing as part of the result and what it is not. Now, say I add another constraint, something like I want to look at only taxi trips where the duration is greater than 10 minutes or duration is less than 5 minutes, right? So again, I can use data cube-based structures, but then I would have to add one more dimension to the cube. Or instead of just count, if I say average fare, now I need to add another dimension to the cube. So literally, there is a space explosion. So just to give an idea as to how much space the nanocubes, which is supposed to be efficient data cube structure in terms of space, so for 1 year of taxi data and computing it just for the space and time, it takes over 40 GB, just storing it, right? And computing this also takes a few hours. So given this, each time, I mean, if I just have to compute it for all the data, then there's going to be a lot of preprocessing time and I need a lot of memory, right? So it is not practical. The original data is, again, including all attributes, is in binary format is roughly for 5 years, no, for 2 years, it is like 30 n.GB, or 30 or less. But this is just for 3 attributes, since it's storing the aggregation for different possibilities, for different regions, and so on. So this is really not a practical thing, especially if I want to do some analysis and I don't have access to huge clusters or huge hardware, right? And here, if in the demo, like I said, I loaded 2 years of data for all of them. And I managed to run it on my laptop. Nothing was pre-computed. The queries were on my laptop, and it was instantaneous, right? And of course, the obvious question you can ask is why not use existing databases? So all databases now have a spatial extension to it. Postgres has PostGIS. Similarly, DB2 has its own spatial extension. SQL Server has, Oracle has, all of them have, right? And there are also new databases, GPU-based databases like MapD that have come out for analytics, which again kind of allow to do these kind of queries. So one of the main problems is, let's look at how these databases in general execute this query, right? So typically, it would use an index for one of the data sets. So here, for example, say I create an index on the neighborhood polygons, and then from the taxi, it would again do a selection. Here again, there could be a potential index if for the other attributes over here, and then it does an index-based join over here. And this join involves point and polygon tests. It has to, typically it's two-step. They first do a filter based on a bounding box of the different polygons, and then they do the point and polygon test. But even in the best case scenario, the most, if you already know these points are in the polygon, so that is the best case scenario where the minimum number of point and polygon tests is all the points that fall inside the polygon, right? And each of these tests is linear in the size of the polygon. So it's actually expensive. If you want to do millions of these, it is going to be quite expensive. And again, the polygons aren't simple shapes. They are much more complex polygons of arbitrary shapes, right? And I think in the neighborhoods data that we use, the average size of the polygon was something like 260 edges or so. So, and it gets expensive, and more. And the other problem is also that the way, because it views the whole data from more like a relational perspective, like a traditional, it doesn't take into account or see that there is some sort of geometry involved, right? It does the join, so, and it does it materializes the join. Basically, you have the result of the join, and then you do the aggregation. So that also requires more space, and then to do it and more time, obviously, right? And I'm being very generous here when I say that this query takes several minutes. So on a tuned commercial database, which I won't be naming, running a query on 5 years of taxi data, which is like 850 million trips and just 10 polygons, it was running for over 15 to 20 minutes, and I just got bored and I killed the process. And I literally struggled to tune the databases for over 2 to 3 weeks, just to get it much more faster than what it was before. Right? And of course, the other possibility of doing this is doing something like index join, or but on the taxi. So I can have a spatial index on the taxi points, and what I can do is for each neighborhood, I can do a select using that index. And this also takes several minutes, or even if you use really efficient indices, it still takes, since you have to run, literally in this case, neighborhoods, we have 260 polygons, you need to run 260 queries. And even if each query is a few seconds, then you have several minutes that require, you need a few minutes at least to do these queries, which is not good for interactivity, right? So ideally what we want is, in addition to interactive response times, we also want to avoid costly pre-processing like, say, the data cube-based structures, and approximations are tolerable, right? So from a visual perspective, especially when you're visualizing all this, if the value is 1 million or 1,000,005, it really doesn't matter. At least the color you're going to view is going to be roughly the same. Or in general, it is okay, right? And like I showed in the demo, we are able to do all of this running on my laptop with limited RAM. So it has 16 GB RAM. And everything is on the laptop over here on disk. And we could get interactive speed. So how did we actually get that? So, questions before I continue to how we do. Okay. So to explain our technique over here, let's look at the simple example, which has 3 polygons and around 30 points. And visually, what do we mean by spatial join and a group by over here? So essentially what I can think of it is I can have something like a simple canvas. So here this screen is a canvas, and I have drawn the polygons over here, I have drawn the points over here, and then I'm just looking at all points inside this polygon and counting them over here, right? So essentially you can think of it visually as some sort of drawing which you have kind of blended together and then you're counting it. And that's essentially the main idea behind our technique, is to kind of draw all of these and proceed. And to keep it simple, think of it as you're using some sort of brush with a particular thickness. So in this case, the thickness is like equal to the size of this square over here, right? So when I have a point, I draw a point over here, which basically means I fill that grid cell over there. And as I draw a point with that thick brush, I keep count of how many points are there in each location. So here I can, so now there's 1 point, so I keep track of it as 1. Then here there's another one. So here when I draw, I know there's one already there. Now I'm drawing a new point, so I increase my calculation, right? And I can do it for all the points, and basically I keep accumulating values as I keep drawing all the points. Now in the same canvas, now all I have to do is draw the polygon and see how to go about it. So I use the same thick brush, and then I start basically coloring inside this polygon over here. So I start here, I don't see any point over there, so it's fine. And then as I keep moving, I know there are 2, so I keep track of it. Now there's 1 more, there's 1 more, there are 2 more. And once I finish drawing this polygon over here with my thick brush, I get the count, which is 15, right? And of course, because I'm using some sort of a thick brush over here, I will count some of the points that are slightly outside this polygon, right? So this kind of, again, gives us some sort of an approximation to the result. So is there some way we can actually bound this approximation? And yes, you can. So depending on how thick a brush that you're using, so you're going to have some sort of an approximate polygon over here. And if you compute and if you are okay with the distance between this approximate polygon and the actual polygon is pretty small, then it's fine, right? So you can actually bound that distance using this geometric measure called Hausdorff distance between the approximate and the accurate polygon. And why is this kind of approximation really okay, or this kind of bound okay, is that if you look at least in a lot of cases, right? So if you just look at Manhattan over here and the neighborhood boundaries, you can see that all the boundaries fall on the middle of the streets, on the roads, right? And so whether there's a taxi that is on the right or the left of it is really okay. It can belong to either of those neighborhoods. It's kind of a fuzzy kind of boundary. And so if the polygon just extends a little to the right or to the left over here, that is fine. So we guarantee that those that are totally inside is always counted. Those that are on the boundary is counted to at least one of them, right? And this is true even when you look at other kinds of things. So for example, you take state boundaries or county boundaries. Again, state boundaries, whether it is even like 100 meters to the one side or the other side of a boundary, a given point, it is okay. You have this kind of fuzziness that is involved, right? And so essentially using this drawing idea and having this approximation with this thick kind of pen over there is what we did. And so the algorithm is just 2 steps. The first step is we draw all the points. The second step is we draw all the polygons. You define the thickness of your brush or pen based on what accuracy bound you want. And why is this efficient, and why does it give us such amazing speed up compared to existing techniques? Is because, I mean, computer graphics has essentially been trying to optimize these drawing operations for the past few decades, right? They can do it extremely fast, especially using the rasterization that is involved. So what I'm doing here, this involves no point in polygon tests at all, right? And so given a polygon, when I'm drawing the polygon, the rasterization pipeline over there actually rasterizes, which basically converts each polygon into a set of pixels, and it does it in parallel using the GPUs, right? So, and we just want to make use of it, and just by looking at this whole spatial queries more from a graphics or a geometric point of view, instead of looking at it from a relational point of view, you can gain this amazing speed up, right? And I'll come to what is the speed up we get quantitatively later on. And of course, there are cases when you want to do much more detailed analysis, you would still want accuracy, right? I don't want approximate, I want the accurate results. And you can still do that using a very similar technique. So here, essentially, the key idea here is we notice that the error occurs only at the boundaries of the polygons, right? So all we need to do is let's identify the boundaries and make sure the points that fall on the boundaries are always counted correctly. So we do point and polygon tests only on points falling on the boundaries. So this also decreases the number of such tests that you need to do from all the points to just a few points over here, right? And so you can find, so here in this case, you would find one is inside, the other three are outside, and you would get the accurate result. Okay. So essentially here, instead of 2 steps, we do 3 steps. We first draw the polygon boundaries, and once you draw the boundaries, you draw the set of points, and while drawing the points, if you find that, okay, the points fall on the boundary, then you do a point polygon test. Again, there is an analogy even in the graphics perspective, so you can think of this as more like using ray tracing in some sense. It's just that ray tracing is does it efficiently even for 3D, but here, since you're working with 2D, it becomes a much more easier kind of option. And for doing this efficiently, you might need a polygon index, which you can again create it on the fly using the GPUs again. Right. And the third step is once we have that, we draw the polygons and we accumulate only values that do not fall on the boundary. So this way you get the accuracy. So how fast are these? What is the kind of time that we get? Right. So all this was implemented on OpenGL, and at least for testing this, we use 5 years of taxi data, which has over 800 million points, and then the NYC neighborhoods, which has around 260 polygons. So you can actually see all the neighborhoods have some crazy shapes over here, right? And all the experiments were run on the laptop that I'm using to present right now, which has a Intel Core i7 at 2.6 gigahertz, 16 GB RAM, and NVIDIA GTX 1060 mobile graphics card, right? And for people who are interested, the code is available online, and we have also put in the data that we use for the experiments online, so you can just download it, run it, compile and run it. And it runs on Windows and Linux. Right. So let's look at the speed up. So we also have, we implemented a CPU, single core CPU version of point and polygon test using a polygon index. And that was without doing the materialization and so on. So it was really fast. So we used that as a CPU baseline. And the black line here is basically the GPU baseline, which again uses the index join, uses an index on the polygons and does a point and polygon test in parallel to compute the result. And the blue is just a multi-core version. We use OpenMP on the single core, and so that's like the potential speed up you would get when you just have CPU. So as you can see over here, this is the bounded one, and we use a bound of 10 meters for all our experiments, and we get roughly 300 times speed up over the CPU version, right? And if you look at even the accurate version, it is still better than doing a brute force. So it lies somewhere in between. So what does this actually translate to actual numbers? So we have divided the numbers as the memory time, so transfer between CPU and GPU, and the processing time on the GPU, right? So here you can see that even for around 850 million points and 260 neighborhoods, the bounded version takes just 1.1 seconds. Right. And all the queries that I was doing over here for a subset of this data, and it's going to be much more faster. And you could, that's one of the reasons why you could see interactive speeds during the demo. This is a GPU baseline. So where we do a brute force point and polygon tests for all the points, and we use a polygon index to do that efficiently. So for each point, we look at all the polygons that fall. We query all the polygons that potentially intersect using the index, and then. Oh yeah, so the accurate was the one wherein we used this technique. So here the point and polygon test is reduced. We do that only for those on the boundaries. We don't need to do it for the internals. And again, when you look at the bounded over here, it's roughly the time is split between memory transfer and the GPU processing. And with new GPUs coming in and faster memory bandwidth that's available, this is just going to improve. No. So here again, yes. So the pixel size, if you have a smaller pixel size, the number of point and polygon tests would reduce. You go to 0 as in? Yeah. It's going to, yes, you can do that too. Yeah, I mean, I won't be showing those details. You can actually keep reducing pixel size and you get pretty good accuracy. But this is essentially my next slide over here, which shows how accurate this is. And here, this is with a bound of 20 meters along each side. And x-axis here shows the accurate values, and the y-axis, the approximate values we compute. And it literally falls on the diagonal, the values that we compute. And if you still want something like, I want the estimate, you're saying that, yes, in this case it is true, but I still want a bound of within what it's going to fall. We can also compute those bounds, which is like, you can see very small red lines over here, the bars, we can compute it, and it takes less than a millisecond more to just add that computation into it. Right? So it's pretty accurate even for the large bound of 20 meters. And yeah, you can look at the paper. We have other kind of experiments on the accuracy, like as you keep decreasing the pixel size, how the time varies for the bounded version and how the accuracy is improved. Approximating the polygon by rectangles is going to be very, very approximate, right? No, but you, I mean, think of something like a diagonal polygon over here. If you have a rectangle that's approximated by it, you have a lot of open space. So that's not going to be, I mean, that's using just the MBR, that's what you mean. Yeah, using the MBR, you're not going to get accuracy at all. That's obvious, but then you also have no control over the accuracy, right? So that's just something like range queries, literally, on in a spatial sense. Yeah, but the boundaries don't matter, as in whether it's left or right on the same street is fine. So if this is a street, whether a taxi is there or there, I'm okay. But because of the way the range is, I can have something that's, say, somewhere near Vijay over there, or which is quite far, right? And that I don't want. I don't have control. Oh, by multiple MBRs. Yeah, but even there, that's essentially what we are doing in a more efficient way. You can do that even for the baseline, but the baseline we wanted to show is more like existing techniques. How fast would that be, and how this new thing would be, of course. Yeah. Yes, so yes, that is true. So it depends on the distribution of the data. And in a way, the data sets, so there's another experiment we did using the Twitter data and the whole of US, for example. So again, these aren't, even the taxi data is not uniformly distributed, right? So it is fine. So that's why computing the error bound would be interesting if you really want it. And even there, since we are looking at just a single pixel, so the error occurs only on a pixel that falls on the boundary, right? So in a way, we assume that within the pixel, it's uniformly distributed. That's like a reasonable assumption, and most data sets kind of worked out as fine. What do you mean by boundary testing? Yes. Testing if it's on a boundary or not, yes. Testing if a pixel falls on a boundary or not is, yeah, it's pretty simple, and we get it by just drawing the boundary over the GPU. No, but then you're just testing if a pixel is on the boundary, right? What else are you testing? Here, point in polygon, you're testing for all points that fall in a pixel. So the number of tests over there depends on the number of points that are there. And I'll quickly just, so this is one of the types of queries that are in, so am I out of time? Okay, fine. Then I'll skip this. Again, even selection queries, we have ways in which you can get sub-second, sub-millisecond almost, no, not sub-millisecond, sub-second times. I'll skip this. I just want to show this final video. So this is again kind of, so the Urbane tool as such itself is like, it's more like a framework that we have built using which you can do a lot of other analysis. Now, since this allows like replacing buildings and it has all the geometry, you can plug in new algorithms to do different kinds of analysis. And one such analysis is like shadow analysis. So let's see if the video works. Yes, okay. So here what we are interested in is accumulating shadows over a given time period and see how the impact is with changing new buildings. So here you can just change the time duration or select a region of interest you want to analyze, right? Or in this case, what you can do is you can actually replace some of the buildings with existing towers. These are actual towers that are being built in New York City. And then you can see how shadows over a given time period kind of impacts the whole range. And you see that at least for these new towers, the impact is in that small region over there and things like that. And again, you could use existing techniques to do that quickly, but again, it's not going to be interactive. And so we have a new way of computing this accumulation, which is we get over 70 times speed up over existing techniques, right? And you can actually, the same data was also used, and there's a web-based interface wherein you can explore the kind of shadows at different times of the year in New York. So this was done by Upshot, the Upshot part of New York Times. And there's a nice visual tool over there. You can actually go there and play with the shadow analysis, right? And again, going to skip. And of course, this is just something like a tip of the iceberg right now. There are plenty of other challenges in urban data analysis, especially in databases itself. Is like here we are looking at one simple query, spatial aggregation, but you can have nested spatial queries, which becomes more and more complex. So how do you can you still attain interactivity using something like this, especially if you want to use it for visual analysis, right? And again, even in visualization, depending on what you want to analyze, you would potentially need new visual metaphors or novel query interfaces to make it easier for users to do queries to answer their questions, right? And yeah, I'll stop with that. And of course, a lot of this work has been going on for like 4 to 5 years with a lot of people, students, postdocs, and other collaborators, part of our lab. And like I said, so our group is like the Vida Center. It's a visualization and data analysis lab at NYU. Yeah, thank you. Yes. We used a shape that was, again, the neighborhoods. So, I mean, that's one of the reasons. If it was just range queries, yes, you could do a lot of approximations. Or you can have a much more efficient kind of thing. You can just create something like an artery and you can proceed, right? And even testing is easy. It's just 2 comparisons. And but in a lot of cases, the kind of data we need is something like this. Polygons over there. And so this makes it complex. this was the shapes that we used for the scaling. We also have other experiments in the paper wherein just to see how with the number of polygons, since we wanted something like potentially up to, I think we went up to 1 million polygons or so, or maybe less. I don't remember the exact numbers, but there what we did was we randomly placed points, computed the Werner diagram, and then randomly merged adjacent Werner diagrams to create some complex shapes, and then we did the experiments to look at it. If there's data and the kind of questions can be answered, then yes. Yeah, that's the thing, right? So at least for the map and rough structure of the 3D buildings over here, I think OpenStreetMap has it. I still haven't downloaded that data. But depending on what kind of questions you want to ask by the impact, if there's additional data, it should be easy to plug it in over here.